Okay, so we're going to talk about something called neural networks. And to do that, we need to know a little bit of calculus. Calculus means this. Suppose we have y equals x squared. Then we write dy dx equals 2x. Or sometimes we do it like this. We either write dy dx equals 2x, or we say y prime equals 2x. Okay. Well, so I have to, since there are a few people who haven't seen it, I should explain it briefly, even though most of us have seen it. So let me start out with that. So what this is called calculus in English, calculus. And this thing here has a name. Pardon me, it's called the derivative. Okay, so anyway, if we take this and we graph it, I think everybody can do that part. Y equals x squared looks like, well, excuse my graph, but looks like that, right? So that's y equals x squared. Now, also, I think most people are familiar with the concept of, if you have a circle and I say, here's a point on the circle, and I say, where's the tangent line to that circle? So, so the tangent line means, maybe I'll use this thing, shapes. Let's see if I can do this. Well, you can see that I didn't do that too well, but means that. That's called the tangent line to the circle at that point. So the tangent line only touches the circle at one place. And so that's called a tangent line to the circle at the green dot. Okay, now thing is, we're not really limited to just talking about in high school. We usually only talk about tangents of circles, but we're really not limited to just circles. We could have some other shape like that, and we could still talk about the tangent line, say at a certain place like here, and we could still just draw it. Let's see if I can do that again. All right. Well, you know what I mean. So that's supposed to be the tangent line, but that didn't even touch. But okay, so we can still talk about the tangent line. It doesn't have to be on a circle, really. So now, in this example here, y equals x squared, let's take a different example first. Let's just take y equals 3x plus 2, for example. So let's do that. So here's 1 and here's 2. And we know that this is going to go through this point because it has a y-intercept of 2. So, and then we know that if we move over 1, 2, 3 units, that this is going to increase by, I'm sorry, if we move over 1 unit, this is going to increase by 3. 1, 2, 3. So this is 4, 5, 6. No, that's wrong. So 3, 4. Let me change that, sorry. Whoops. That's supposed to be 5, right? 2, 3, 4, 5. So we know that if we move over 1 unit here, we go up 3 units here. So the next point is going to be here, and then the next point is going to be up higher. And we're going to have a line like, let's say this. We're going, well, let's say this. Okay, we're going to have a line for the graph of y equals 3x plus 2 is going to be something like, well, okay, so it didn't fit very well, but you know what I'm talking about, right? So that's the line for this, right? Okay, and then we can ask for the slope of this line. So we can say, what's the slope? Right, everybody knows this. And the slope, of course, is 3. And the slope means, when you go to the right, how much does y increase? That's called the slope. And we all know about that. So we know that the slope is 3. Now, but the slope has another name besides being the slope. It's also called the slope is also called the rate of change, right? That's the slope, means the rate of change. How much does y change when we change x? It's called the rate of change, or actually it's called the average rate of change. So the slope is the average rate of change. So now going back to this picture that we just had, going back to this one, and if we do y equals x squared, we can sort of talk about the same thing, but not for a straight line. Now, I really can't draw this very well. Okay, so we could talk about this same thing here. The slope, but here. Now, what do we mean by that? Well, we mean the kind of rate of change. So like if we start here and we move over by, say, 1 unit, suppose this is 1 unit, then how much increase do we get? And that could be, that we could talk about the rate of change there. So let's say this is 1 and 2. So the height of this is 1, and the height of this is supposed to be 4, right? Because 2 squared is 4. So, so the rate of change here, or actually the average rate of change here, is this distance is 4, and this distance is 1, so it's 4 over 1, which is 4. So the rate of change here is 4. However, the problem is, so we can do that, but the problem is if we do it somewhere else, we're going to get a different rate of change. So like here, if we go from 2 to 3, now this is 4, this height is 4, but this height is 9. So now when we move over 1 unit, or here actually, when we move over 1 unit, we're moving up how many units? From 4 to 9 is 5 units. So the rate of change is 5 over 1, or 5. So the rate of change is different depending on where we do this. That wasn't true here. In this case, the rate of change for a straight line is always the same, okay? But in a case of a curve, it's not always the same. It's different depending on where you are. So what we say is, we say, okay, suppose like here, if I say, okay, what's the slope, right? What is this, 1 here? What's the slope right here? Well, everybody knows the answer to that. The original line was y equals, I think it was 3x plus 2. So if I ask you what was the slope there, right here, of course, the answer is 3. And then if I ask you what's the slope there, the answer is still 3. It's always 3. The slope of a straight line is like this is 3. It's 3 everywhere. But here, it's not the same everywhere. So instead of, but we still want to sort of be able to answer the question, what is the slope? Or what is the slope at a particular place? So suppose I want to say, what is the slope right here? So how do I answer that? Like, there's not a good answer for that, right? Because if I move to the right here, I get 5. But if I move to the left here, I get whatever we got, 4. It's not the same. So there's not a good answer. So what we say is, okay, let's make up an answer. I mean, let's make up a way to say what we mean by the slope right here, right at this red dot. And what we're going to say is, what we're going to mean is, by the slope there is, wait, let me have a different color here. I guess here. What we're going to mean by the slope is this. Okay, I'm not too good at this, so but I hope you know what I'm talking about. What am I talking about? What do I mean by the slope there? I mean the slope of the tangent line. Okay, so that's what I mean by the slope for a curve. A curve, you can still talk about the tangent line. So what I'm going to mean by the slope is at the red dot for the white curve, for the parabola curve, what I'm going to mean by the slope is the slope of the tangent line. So I don't know if I can find that, but that's what I mean by it. I don't know if we can actually find the slope of that pink tangent line, fuchsia tangent line, but if I could, then I would say I know the slope at the red dot. Okay, is this clear to everybody? Does anybody not understand what I'm talking about? Okay, so now we have a concept for slope of any kind of shape. So it could be this shape, or could be any other shape. Could be like, suppose we had this curve. We just say, okay, what's the slope here? I just mean the slope of the tangent line there. Now I don't know that I can find that because how do I find it? I have no idea how to find it. But if I could find it, then I'd say I know the slope there. Or what's the slope here? Okay, I mean the slope of the tangent line there, and so on. So now we have a concept or a definition for the slope of a not just of a straight line like this one, but of a curved line like this one. Okay, now actually in calculus we figure out how to find those slopes. We can actually find the slope of a curved line. So if we go back to y equals x squared, there's something called the derivative, which we can write either like this, dy over dx, or in some other times we call it just y. We call it just y prime. And that is a formula that will tell us the slope. So remember, we're trying to know the slope, let's say, of this function, which looks like this. And we're going to have a formula. Now, the formula, in this case, for this particular function, turns out to be 2x, or 2x. So that's going to tell me the slope. So in other words, what do I mean by that? Suppose I want to know the slope when y equals 3. So y equals 3 is right here. I want to know the slope there. So I want to know basically the slope of the tangent line there. So how is this going to tell me that? Well, it's easy. What this formula means is just tell me what the x coordinate is. So this is y equals x squared. So the coordinate of this point is what? 3, comma 9, right? X squared is 9. So that's 3, comma 9. But you don't, to find this formula only requires that you tell it the X coordinate. So I don't need the 9. I just need the 3. And I put that in here. And so that says that the slope is 2 times 3. In other words, the slope of this line will turn out to be m equals 6. The slope is 6. Okay, so this formula tells me the slope at any place. For example, here, suppose this is -2. Well, we already can see visually that the slope is not going to be positive here. It's going to be negative, right? The slope of this line is not positive, it's negative. And let's check our formula. So the formula says, tell me the x value, and I'll tell you the slope. So the x value is -2. If I put in -2 here, I get -4. Well, at least it was negative, and we did require it to be negative. And also we can do it the same, just do another check right here. Oh, this is supposed to, you know where that's supposed to be. But what's the slope here? Well, you can see that the tangent line is flat, so the slope should be 0. And this is when x equals 0. So we're supposed to put in 0 in here, and we do get 0. So at least it looks like it's working. Okay, so this derivative tells us the slope. And that, remember we said slope is the average rate of change. But here, this is the rate of change right at this one point. So we call it the instantaneous rate of change. How do I spell it? Instantaneous, is that right? Instantaneous, is that right? Instantaneous, yeah. Rate of change. So the derivative of this thing gives us this, the instantaneous rate of change. So it's instantaneous in the sense that it's at each point it's different, and the derivative tells us at any point. So that's called the instantaneous rate of change. Okay, so that's what the derivative means in calculus. So that's a very quick introduction to the derivative. Now, how did I get that formula? I mean, how did I know that when I start with this to get the derivative, turns out that y prime, or dy dx, is equal to 2x. Well, that you have to learn, how to do these, to figure these out. So like, for example, this one, if we had that function, which looks like, if you remember, looks like this. Anyway, if you had that function, this function, the formula is different, obviously. The derivatives are going to be different. The slopes are going to be different. So y prime, or if you prefer this notation, you can use that, is 3x squared. So it's not the same as this formula. And so on. So there's, you have to figure, in calculus, you learn how to do this, how to figure out what these are. But we don't need to do that. We just need to understand the basic idea. We don't have to find out all the different, if I say, okay, well, how about if you had this function, y equals x to the fifth, what is it? You don't have to do that. We don't need that. We just need to know the idea. The answer is this. But you don't need to know that. You just need to know that this tells you the slope of this. Okay, that's all you need to know. Okay, so that is the concept. Well, actually, I shouldn't say that's all you need to know. But anyway, that's the basic concept of calculus. Okay, now let me ask it once again. How many people did not know this? Please tell me how many people did not know this. 1, 2. 1, 2. Okay, that's a small percentage. That's great. Unfortunately, for the small percentage, it's not so great, but for the rest of us, at least, it's great. Okay. So the next thing is maybe a little confusing for that very small percentage, and I'm sorry, but um, let me bring the screen to here. No, where's that? Okay, a little bit more review. So suppose we have two functions, f of x and g of x. Like, for example, this might be x squared, and this might be x to the fourth. And we want to know the derivative. So we know this, dy dx. So first of all, we can write that notation that we had before. I can write it like this. Remember, the answer was 2x for this. And this is, we can also write it like that. The derivative of x squared is 2x. We can also, I think we did this one also. The derivative of this one, I think we just said, is 3x squared. And I think I also said, anyway, so this is more notation. We already did that. This just means the derivative of the x cubed function is 3x squared. This means the derivative of the x squared function is 2x. If we wanted to know the derivative of the x to the fourth function, we would write that. And the answer turns out to be x cubed. But as I said, we don't know how to do these. We didn't talk about that. But these are part of a calculus course. And then now, suppose I have this function f and this function g, and I want to know the derivative of of the two of them together, of f plus g. So I want to know this, the derivative of the sum. So that means, for this case, I want to know the derivative of the sum of them, x squared plus x to the fourth. So I don't know how to do that. But there's a rule that says that you can do this. The derivative of a sum is the derivative of the first one plus the derivative of the second one. So using that rule, if I want to know the derivative of this rule says I can do the derivative of the first one plus the derivative of the second one. That means I can do this, dx squared, like that. That means the derivative of the x squared one. I'm just using different notation all over the place here. I'm sorry about that. But this just means the derivative of the second one, of the first one, plus the derivative of the second one, like that. So we already know this, and we already know this. So we already know that this is 2x. We already know that this one we said was 4x cubed. So now we were able to do this. Or this, we're able to do the sum of these two. And this rule is true no matter what the functions are. So if g turned out wasn't x to the fourth, but x to the 40th, the rule would still work. So we'd still say the derivative of the first plus the derivative of the second. So the derivative of this would be the derivative of the first plus the derivative of the second. So whatever this was, it would be different now. It would just be this one plus that one. So that's called the sum rule, S-U-M, right? Because this is sum. And we also have a rule for differences, which is almost exactly the same. The derivative of f of x minus g of x. And there's a rule for that also, and it's almost exactly the same as this rule. It's equal to the derivative of the first one minus the derivative of the second one. So that's just another, very similar. But we also have a rule for products, f of x times g of x. Now that one is not so simple. It doesn't look so natural. You might say, oh, I think it's going to be the derivative of f times the derivative of g, but that's not right. It doesn't work like that. Unfortunately, it's not that simple. So that's not the rule for this one. It's not equal to that. This was so easy, right? The derivative of f plus g is just the derivative of the first one plus the derivative of the second one. This was equally as easy. The derivative of f minus g is the derivative of the first one minus the derivative of the second one. But this one is not so simple. It turns out to be different. Anyway, we don't care about it right now, what it is, because what we want to move on to is a different rule. And that is, remember, so if we have two functions, f of x and g of x, we can talk about the sum, we can talk about the difference, we can talk about the product of two functions, we can talk about the quotient, means division, quotient. So this means f plus g, this means f minus g, this means f times g, and this means f divided by g. And we can talk about all of these. So like if we have x squared and x to the fourth, we can talk about x plus that. We can talk about x squared minus x to the fourth. We can talk about we can talk about x squared times x to the fourth. And we can talk about x squared divided by x to the fourth. No problem. Right? These are all natural things to do. Now we also have, though, another operation. These are called operations, different operations, sum, difference, product, and quotient. But we have another operation called composition. So that's not this one, not this one, not this one, and not this one. Composition is different. So what do I mean by composition? I mean that we do f of g of x. So what does that mean? Let's suppose that f of x is equal to x to the squared. Okay, so I can say, well, what is f of 1? And everybody knows the answer, it's 1 squared. What is f of 2? Everybody knows the answer, it's 2 squared. What is f of 3? Everybody knows the answer, it's 3 squared. What is f of 10? Everybody knows the answer, it's 10 squared. What is f of a? Everybody knows the answer, it's a squared. What is f of b? Everybody knows the answer, it's b squared. Now, how about if I say, what is f of a plus b? So hopefully you know that just means that you take a plus b and square it, because the rule says whatever you put in, you square it, square it, square it, square it, square it, square it. So if you put this in, you should square that. So f of a plus b means a plus b squared. So if I write this, I'm putting g in. So I don't know what g is, maybe whatever g is, but whatever it is, I'm just supposed to do what? I'm just supposed to square it, same as here. Okay, now let's suppose we had a different g. I think before we said g was x to the fourth, but let's take a different g just to make this example clearer. Let's suppose g equals x plus 8. Okay, so what does this mean? If I want to know, here's f, f is x squared, and there's g. So I want to know f of g of x. Well, let's go back just before we get to there. No, yeah, let's go back. So let me go back to that. Let me say here, let's write it again. F equals x squared, x squared, and g equals x plus 8. Okay, so let's just go back. What does f plus g mean? So it means x squared plus x plus 8. Okay, that's good. What does f minus g mean? Okay, that means what? X squared minus x plus 8. Okay, that's good. Okay, what does f times g mean? That's x squared times x plus 8. Okay, so we know what these mean. Now, what does this mean? F of g of x. Well, we already said it just means, so f is x squared. So it means we should square. We just said that it means we should take g of x and square it. That's what we said right here. Now, what is g, though? G is here.
So x plus
So what
8
is that?
squared.
So g is, so we should square g. And what is g? X plus 8. So what is f of x? F of g. It's this. So it means you put in g into f. Suppose g was equal to, instead of this one, let's say it was equal to x squared plus 3x plus 5. So what is f of g of x then? Well, f is still the same. So it means whatever it is, I should square it. And then what is it? In this case, I said it was that. So what does it mean? It means that you square what? X squared plus 3x plus 5. So whatever that is, that's what we mean by f of g of x. Okay? So that's the kind. So we said that we had some operations here, which we called sum, difference, product, and quotient. But now we have another operation called composition. That's this. This is called composition. So that's another operation. What do I mean by an operation? It's a way of combining two functions. So this is one way to combine two functions, another way to combine two functions, another way to combine two functions, another way to combine two functions, and another way to combine two functions. So that's what we mean by an operation. And this is a fifth operation, composition. Okay, so we have this fifth operation called composition, and the way and the note, we have notation for the first four, right? What do we mean? F plus G. We have F minus G. We have F times G. We have F slash G. Those are kind of the what do I mean? This is the symbols for these different things, right? F plus G, F minus G, F times G, F divided by G. And for composition, we write it like this, F circle G. So what do I mean by F circle G? I mean this, what I just said. Okay, but the notation is F circle G. Okay, so we'll use that notation to mean this. Okay, F circle G means the composition of F and G. Okay, now going back up to above, we had some rules up here for doing derivatives of different operations. So we had this first rule that said that the derivative of the sum of two functions was here. This was the rule. So the derivative of this, we could do it as the derivative of the first one and the derivative of the second one and just add them. So that was a rule. We had another nice rule, easy rule, the derivative for the difference of two functions. And then we said this one, we didn't give the answer, but we said it's not as easy as this, not so simple like this. It would be nice if it was just this, but it's not. And I didn't give you the actual answer in this case. I don't want to bother with it. You don't need it, and there's no reason to look at it. But it's not as simple as this. And there's also a rule for division. So there's a rule for finding the derivative of a sum. There's a rule for finding the derivative of a difference. There's a rule for finding the derivative of a product. There's a rule for finding the derivative of a quotient. And there's also a rule for finding the derivative of a composition. And that rule has a name too. Like the other ones have simple names like the sum rule, the difference rule, the product rule, and the quotient rule. And this one has a slightly different name. It's called the chain rule. The chain rule. but it's just the chain rule is the name of the rule for this one. So in other words, if I want to know the derivative of f circle g, that's the answer to this. The general rule for this, it has a name. It's called the chain rule. Doesn't matter. You could call it of course, it's probably better to call it the composition rule because that's what it is. But it's also called the chain rule because there's a way to think of it as like a kind of a chain reaction. But anyway, it doesn't matter what it's called, but that is what it's called. It's called the chain rule. So anyway, what is the answer to it? Well, it looks a little complicated. Just like I didn't bother to show you the product rule because that was a little complicated. And this one also looks complicated, but this one we need it, so I have to write it out. So what is it? The derivative of the composition of two functions. What is the answer? So you might think, oh, well, I don't know what you might think. But anyway, the answer is, now I'm going to stop using this notation. So remember we said that there are two notations. Well, I could use this notation actually, but okay, I guess I should since we started it. So let me just rewrite this before I give you the answer. I'm asking for what's the derivative of f of g of x. So I just rewrote this like that. Okay, now the answer is this. One way to write the answer, if we use this notation, the way to write the answer is, remember, there's another way to write this question, and that is f circle g prime. Remember, we said way up at the top, in fact, as far as I understand it, in China, they don't use this d dx or d, they don't use this notation. They use only, like in the United States, we use either notation. But in China, they don't use this notation. They use this notation, y prime. So I could use this notation, y prime, instead of this. So whatever notation we use, though, of course, the chain rule should be the same no matter what notation we use. But anyway, these are both the same thing. So I could say, instead of what is this, I could write it like this. What's the derivative of the composition? Or same thing, what's the derivative of the composition? So I could write it either way. Now, if I write it this way, then I should keep going to give the answer this way as well. But this way, the answer looks a little bit strange. We'd say it's, well, I don't know. This definitely looks strange. But it's df d, I guess I'll write it like this, dg. You know what I mean by, I'm not putting the arguments in here. I'm just putting the name f. Like I'm writing f, I'm not writing f of x. Okay, so if I write that way, then it doesn't look so bad. If I write it this way instead of this way, this won't look quite as confusing. So let me write it this way. df dg dg dx. So that's the answer to the derivative of a composition. It's df dg dg dx, but this is a little confusing. But anyway, you can see why it's called the chain rule, because there's sort of a chain reaction here. Or maybe you don't see that. Maybe that's not so clear, actually. But anyway, you could sort of see like this is being canceled with that, which isn't actually exactly right, but it looks like it's right. And it looks like, oh yeah, that's the derivative of f. Okay, anyway, I'll just say that. But I can also write it in terms of this way. And then what we get is the same answer as this, but we're using different notations, so it's going to look different. It turns out to be this, f prime of g of x. Now, I know this is confusing for someone who's never seen this before. Like, I can't teach the whole course in calculus. Times g prime of x. So these are the same, just different notation, and maybe that's not very clear. But this is also the same rule, actually, just written differently. So this is called the chain rule, and this is also called the same chain rule, just two different ways of writing it. And I can understand that that may not be that clear, but it is true. Okay, so that is the chain rule. And we need this. This is essential for neural networks or for deep learning. Everything depends on this one thing, on the chain rule. The neural network is basically just the chain rule, more or less. So that's why I spent this time talking about it. So it's called the chain rule. Let's just do some examples of this. Suppose we had x cubed for f, and g of x is equal to x squared plus 8. Okay, so we could say, I want to know the derivative, or let me make this come more relevant. Let's say that was the original f. So f is x to the 30th. So I want to know the derivative of f of g, like that. I want to know the derivative of that. Now, so what I'm saying is I want to know the derivative of what? I want to know here, what is f of g? So the answer to that is what? So g says raise something to the 30th power. G says raise something to the 30th power. And I don't have enough room here. G says raise something to the 30th power. And what is it? I'm sorry, F says raise something to the 30th power. And G is what? I'm raising what to the 30th power? G. And G is what? It's x squared plus 8. So suppose I want the derivative of that. Okay, well, that looks pretty complicated to find the derivative of that. But I can use the chain rule to make it a lot easier. So one way to find the derivative of this would be to multiply this thing out 30 times. And then I'd have a very, very long polynomial. And I could sort of get the derivative of that polynomial. But that seems like a crazy amount of work to do. And the chain rule allows us to do it much more easily than that. So I could do it like that, though. I could just multiply this out 30 times and have a super long polynomial. And then I could take the derivative of each piece of that, and I'd get the answer to the derivative of the whole thing. But that seems like a crazy amount of work to do. But the chain rule says I can do it a different way. It says I can do it like this. So what does that mean here? So what does this piece mean? And what does this piece mean? Well, actually, this piece is the easier of the two pieces. So let's do that first. So let's do that first. So let's do the first part, G prime. So what is that? Well, where's G? Here's G. So we're going to have two pieces. And we're doing this piece first because it's easier here. So we want G prime. And what is G prime? Well, that's easy. So can somebody tell me what G prime is?
Is the gx squared plus 8, Professor?
Say it again. Yeah, what's the derivative of this one?
It's 2x, Professor.
2x. Good. That's right. So those of you who know calculus, you know that answer. The two of those who didn't really know calculus don't really know that. But everybody else probably knows that this is 2x. Okay, so that was the easier one. This one looks pretty easy. Now, the thing is, what does this part here mean? What what does this mean? So we have to figure out what that means. It's not so complicated once you understand what it means. So in other words, what does this mean? Okay, so it's a little bit confusing notation here, but once you understand what it means, it's easy to do it. So what does it mean? Well, what it means is simply that you take the derivative of f. Okay, and here's f, and you take the derivative of that. Well, that's not too hard to do. What is the derivative of this? Can somebody tell me what the derivative of this is?
It's 30x to the 29th power.
Okay, good, thank you. So, you know, I think most, like I said, except for the two people who haven't studied this, most of us know that it's 30x to the 29th. So that's not very hard to do. So that's what this means. It means take the derivative of f. Now the only difference is it doesn't mean this, f prime of x, which is what we just did here. Doesn't quite mean that because it doesn't say that. It doesn't say f prime of x. It says f prime of g of x. So what does that mean? That means that instead of x, we just put in g into here. So what does that mean? That means we just take 30 and then something to the 29th like we have, but it's not x to the 29th, it's g to the 29th. So what do I put in here? I put in g, not, well, I could put in g right here, like that. But I can also just write out what g is. What do I get? I get 30, but I can just write out g. What was g? I forget. G was here. So it's just 30, and then you put in g, and that's the answer. Now remember, we had another way to do this, which was, what did we say? We could here, I said, well, if we want to find the derivative of this, we could just multiply that out 30 times. And then we'd get a huge polynomial, and then we could figure out each piece of it. But of course, that would be horrible. But now we got the answer much more easily than that by just using the formula. This formula, well, sorry, it's, sorry, I made a mistake. We have two pieces to the formula. Where's the formula again? Here. Here's the formula. And we did this piece first, which was easy. That was just 2x. And now we're working on this piece, which we just did, and we got here, or here. We got here. So we just did that piece, and now the answer is a lot easier than that long thing that we were thinking about doing. I just have to take this piece and put it in there. I don't have enough room to write it nicely, so I'll just say that. I'll just use the arrow. So it's just going to be this times this. There's going to be this one times this one, and that's the answer. So that is the example of using the chain rule to find the derivative of this thing here. In other words, we have a g, an f, and a g, and we want the derivative of their composition here. And the chain rule says you can do it like this. And that's how we did it. And we get this piece and this piece, and that's all. So that is the chain rule, an example of it. And the chain rule tells us how to find, the chain rule tells us, how to find the derivative of a composition of two functions. Okay, and the rule, once again, I'll write it the second way. So if I want to know the if I want to know the derivative of f of g of x. So I want the derivative of the whole thing. I'll use that notation to mean the derivative of the whole thing. The answer is f. I'm using this the second way of writing it, like this, times the easier part, which is here. Okay, so that's called the chain rule, and that is at the very heart of neural networks. So we spent quite a long time on this, which seems like it has nothing to do with data science, and so far it doesn't. It's just a rule for finding derivatives. Remember, though, let's just remind ourselves what we're doing here. Why are we? What in the world are we doing here? We said that suppose we have a curve, and now I'll just make it a general curve, like this, something like that, and I want to know this slope. And by the slope, I mean the slope of the tangent line at that point. So suppose I want to know that. That's called, the derivative tells us that. The derivative tells us the slope. Now, what we just did was, I said, suppose we had some crazy function. I said, suppose that we had a function like this. What was it? It was x squared plus 8 to the 30th. So that's a pretty crazy function. But remember, our function was actually this, because our function was the composition of two simpler functions, but the composition turned out to be this. So this was our function, and I want to know this, what the formula for the slope of this crazy function is. And the chain rule tells me the answer. What was the answer? It was up here somewhere. It was this thing plus this thing, or this thing times this thing, I mean. This thing times this thing. So that's the formula for the derivative. So that's going to tell me the slope of this crazy function wherever I want to know the slope of it. So that's what we're doing. When we use the chain rule, it's just a way of calculating the formula for finding slopes. So yeah, maybe it's a complicated formula and we have to use the chain rule and blah, blah, blah. But finally we get an answer. The answer was, we had two pieces. We have to multiply them together. It's some crazy thing. Who knows what it is? But that tells it, what does that thing finally do? That gives us a way to know the slope. Like, for example, suppose the slope at 10, when x equals 10. So we have a formula here and here. We're going to have to multiply them together. But in the formula, there's going to be an x in here and an x in here and so on. And we just put in 10 for the x and multiply it all out. That's going to give us a number, like say 500 or something, who knows. And that's going to say, oh, the slope when x equals 10 is 500. Okay, so that's what we're doing. We're finding the slope of a curve. And then all this other crazy stuff was just how to find the answer for some crazy function. Okay, so the chain rule, that's what the chain rule is doing for us. What time do we finish today? So that's what the chain rule was doing. It's just telling us how to find the, for crazy functions like this, how to find the slope. It's still all about finding the slope, or what we call the instantaneous rate of change. How quickly is the, how the slope means how quickly is the function increasing at this place. Like here, suppose I have a curve that looks like, this, like that. Now it's increasing very quickly here. It's not increasing as much here, right? The slope here is more than the slope here. So it's increasing faster here than it is here. And that's what we want to know. Now, who cares about how quickly something is increasing? Well, if this is like economics, and this is like the price of a stock, so this is the time, like the days, and this is the price of a stock, what does this mean? It means that on this day, the stock price was increasing. Let's say this is Monday. The stock price was increasing at a certain rate. And on Thursday, say this is Thursday, the stock price was increasing much more. So who cares about that? I don't know. People care about that, right? So the rate of change is important, right? It tells you how fast something is increasing. Or another example, not so exciting example, would be, but the original example actually would be, suppose this is time and this is distance, and we're talking about some ball which is falling from, the top of a building, right? You take a ball and you drop it. You say, well, how fast is it falling? And this is the distance. Now the distance is increasing. The distance it's falling is increasing as time increases. So I'm going to make it increasing. And then you could say, okay, well, what does this mean? What does the slope here mean? It means how fast is the distance increasing here versus how fast is the distance increasing here? So who cares about that? I don't know. Not many people care about balls, but it's just telling us though how fast it's increasing means how fast it's falling, or the speed. So the speed here is the slope here, and the speed here is the slope here. So that might be interesting to a physicist or high school student or something. But anyway, these are rates of change, and they're important. Going back to this example, this is how quickly the price is increasing on Monday and how quickly the price is increasing on Thursday. So that might be important to somebody. So rates of change or slopes are important. And the derivative, if you knew the shape of this curve, not the shape, if you knew the formula for this curve, like suppose it turned out to be y equals x cubed plus 3x plus 5 or something like that, then maybe you could find the derivative. And maybe the derivative turns out to be 3, I'll write it as y prime. Maybe the derivative turns out to be 3x squared plus 3 or something like that, maybe. So whatever it turns out to be, then this will be able to tell you what the slope is here. Monday, let's say Monday was the 5th day, and Tuesday and Thursday was the 7th day or something, whatever, 8th day. So this is the 5th day and the 8th day, whatever. So you'd say, okay, on Monday, how fast was it increasing? Well, you just put in 5 into here, and that would tell you the rate of change here. And then you put in 8 or whatever it should be here, and that would tell you the rate of change here. So the derivative, if you can find it, tells you the rate of change. So that's the end of our discussion about derivatives. Now we've discussed derivatives. Now we can use that concept. And we also, importantly, discussed the chain rule as one of the derivative rules. So we've done all of that. Now we can, and there's just a little bit more math we need to do, very short. And then we can go and talk about neural networks and how they work. But we needed that prelim in math so that we could use it later. So we'll go into neural networks next time, and probably have to spend 2 weeks on it at least, but I'm going to keep it down to 2 weeks. And I'll probably break it up and do some Weka stuff that has nothing to do with that, nothing to do with neural networks, and nothing to do with calculus, and nothing to do with math, but just Weka. We'll do some Weka stuff as well, so that you can improve your reports, because understanding regression and understanding neural networks is not going to improve your reports. It's going to improve your understanding of data science, because but we're only studying like one machine learning algorithm here, neural networks or deep learning. But deep learning is the most important one these days. And then we also studied regression. We also studied J48, but there are many others. And we're only studying a few in depth. And that's not going to help your report. That's just going to help you know what's going on with data science in general. Okay, that's all for today.